Okay, for the lecture today, we will talk about carbon economics. And for this set of slides, we will learn how to to analyze the cost benefits of a carbon reduction strategies. And also, we will use some tools, okay, like calculating the payback period or using life cycle cost analysis to calculate the net present cost of a certain carbon reduction strategies. Something similar to 2 weeks earlier, okay, in the lecture about carbon reduction strategies, we have analyzed different kind of carbon reduction, like using PV panel or maybe using wind turbines. Okay, so for these kind of carbon reduction strategies, there could be some energy saving and therefore energy charge saving, okay, money saving. And we can use a table like this to calculate the net present cost. Like here, this is the net present cost of the solar PV panel in 15 years. Okay, and then using this cost, we will be able to calculate the cost for every 1 ton of carbon dioxide equivalent saving. Okay, this is the cost for every 1 ton of carbon reduction. And I understand that this calculation in this table seems to be a little bit complicated, and this is only for your reference. Okay, this table is for your reference, and it is to introduce one method to do the analysis. And then today we will do something similar, okay, but in a more professional kind of calculations. Okay, and for this table, we have used the term discount rate. Okay, so this the concept of discount rate will also be explained and used in this lecture. Okay. So in the later part of today's lecture, we will learn how to use the discount rate to calculate the net present value and then do some analysis. Okay, so let's start. Okay, why put a price on carbon? So why do we need to care about the cost of carbon? Okay, so first of all, greenhouse gas emissions create negative externalities. Okay, that is some impact on the third party. Okay, for example, the climate impact, and this will affect the ecology or people elsewhere. Okay, and these impacts are usually not reflected in the market price of a product. Okay, the price of the product may reflect the raw material and then the labor cost, the transportation cost, but usually it doesn't include the impact to the environment. Okay, so pricing carbon helps internalize these costs, making polluters accountable for the environmental damage that they cause. Okay, so we want to internalize the price of a product with the impact to the environment. Okay, so like the impact, like the emissions of the greenhouse gases and then causing the climate change and others. So pricing carbon, okay, examples would be the carbon tax. Okay, so the more energy you utilize, and then indirectly it will result in more emissions of carbon. Then you pay a tax according to the amount of emissions. So this is carbon tax. Okay, the more you emit, the more tax you need to pay. And the emissions trading system, ETS. So it is actually introduced in the Kyoto Protocol, and the government or a region, okay, will issue some allowance of emissions to different organizations. So if you can reduce, those allowance means that you are allowed to emit certain amount of carbon emissions, okay? So certain amount. And if you can reduce your carbon emissions such that your actual emissions is less than the allowance, then you can sell these allowance to other organizations, okay? So it gives the organization some financial incentive to invest in like reduction strategies or clean technologies and others. Okay, so carbon tax and emissions trading systems, they are both about placing a price on carbon. Okay, a carbon price provides financial incentives for business and individuals to reduce their emissions. Okay, like in the Kyoto, they created the carbon quota for individual countries. Okay, they have some target set for different countries. By creating a market for carbon emissions, a carbon price can drive investment in research and development of low carbon technologies. Okay, only if there is a price in carbon, okay, it means that only if there is carbon tax, okay, so the more you emit, the more you need to pay, or if you can reduce the emissions, you can sell it for money. Okay, so only if there is financial incentive, then people will invest in green technology. Okay, only when there is benefits, right? So the market can identify the cheapest unit of greenhouse gas to cut and therefore allow the society to fight climate change at the lowest cost. So sustainability is not just about environment. Okay, there are three pillars in sustainability, right? So we have the environment, and then social, and the economic. Okay, so we want to improve the environment. Okay, we want to reduce our impact to the environment, but at the same time, we don't want our economy to collapse. Okay, so in order to reduce the carbon emissions, we want to utilize the cheapest technology first. Okay, so that's why we have to do some analysis to calculate the cost of reduction, the cost of carbon reduction for different kind of technology. Okay, there are many ways to reduce carbon emissions, but which one is the cheapest? Which one is the most cost effective? Okay, this is about today's lecture. Okay, so we have carbon tax and the ETS. So carbon tax, it is the carbon pricing mechanism that directly imposes a tax on the carbon content of the fossil fuels. So the carbon content could be really the amount of carbon inside the fuel. It could also be the amount of carbon dioxide released, okay, when these fossil fuels are burned. So the more carbon dioxide a source emits, the higher the tax it pays. Okay, so just like so earlier the government wants to impose the municipal solid waste charge, right? So the more you throw away, the more you need to pay. Okay, something like this. So for the carbon tax, similar. So the more carbon dioxide you emit, the higher would be the tax. So by imposing a financial cost on carbon emissions, a carbon tax makes emitting carbon dioxide more expensive. Okay, so if you don't use the clean technology, okay, just burn the coal for the manufacturing, then you are emitting more carbon dioxide, and then the whole manufacturing process, okay, or the whole cost of manufacturing the product will be more expensive, okay, because we want to include the impact to the environment, to the cost of that product. So this economic disincentive, encourage business and individuals to switch to cleaner energy sources, invest in low carbon technology, and reduce their carbon footprint. Okay, the ultimate objective is to persuade people, persuade organizations to utilize clean technology, okay, to reduce carbon emissions. And for the emission trading scheme, ETS, it is a market-based approach designed to reduce greenhouse gas emissions by allowing companies to buy and sell allowances that permit them to emit a certain amount of carbon dioxide. Okay, so allowances would be like to allow the organization to emit certain amount of carbon dioxide. Okay, maybe like one allowance means the permit to emit 1 ton of carbon dioxide. Okay, so if you are given certain amount of allowance, then it means like you can emit 1,000 ton. Okay, maybe you have 1,000 allowance, then it means you can emit 1,000 ton of carbon dioxide. And if you utilize some clean technology, carbon reduction strategies, such that you can reduce your emissions to, let's say, 900, then you have 100 extra, and you can sell these allowance to the market, okay, so to generate some revenue. So the government sets a cap on the total emissions. So this year, maybe you are given 1,000. And then next year, the government wants to further reduce the carbon emissions. Then maybe next year, you are given only 950 allowance, okay? Because the government wants to reduce the carbon emissions. And it means that the allowance distributed to every organization will be less and less, all right? So, yeah. Issuing limited numbers of allowance that correspond to this cap. Companies that reduce their emissions below their allocated allowance can sell their surplus credits to others that exceed their limits, creating a financial incentive to lower emissions. So when you reduce your carbon emissions, okay, on one hand, you can reduce maybe energy saving. Okay, so you can pay less for the electricity charge, okay, or energy charge. And on the other hand, you can also sell these extra credits to the market, okay, and to make a profit. And the carbon price fluctuates based on the supply and demand. Okay, so there is no fixed charge or fixed price on every credit. So it's based on supply and demand. So if one year the government sets the cap a little bit high, so every organizations have a lot of credits, then the price of the carbon will be very cheap. Okay, because they don't need it. Okay, they have they don't need to reduce their carbon very much because they are given a lot of credits. Okay, but if another year the government lower the cap, okay, such that every organizations have limited credits, then they have to find ways to reduce their carbon emissions, or they have to buy from the market. So if many organizations wants to buy the credits from the market, then the price of the carbon will be more expensive. Okay, and when the price of the carbon, when the price of every credit is more expensive, then the organization may invest in the technology. Okay, may invest in the clean technology or other renewable energy. Okay, because the price of the carbon is too much, they don't want to pay for buying the credits. Instead, they may invest in the renewable energy or the clean technology. Okay, that's the theory. To encourage more aggressive emissions reductions, the government can tighten the cap. Okay, means lower the cap, reduce the numbers of allowance. Okay, so tighten the cap on total emissions and limit the number of allowance. So the scarcity of allowance will drive up the carbon price. So when there is less allowance for carbon emissions, okay, then you have to buy from the market. Okay, so everyone is buying the allowance from the market, and the price of the carbon will be getting higher. All right, so based on supply and demand. For emissions reductions to be meaningful, the carbon price must be sufficiently high to incentive companies to invest in cleaner technology and practices. So if you want the organizations to invest in renewable energy, okay, they have to pay, right? They have to do some investment. And they will only do investment when it is profitable. Okay, so when the price of every credit, every allowance for emissions is very expensive, then they may switch to investing in the R&D, the research and development for technologies, okay, such that their own carbon emissions can be reduced. Okay, so instead of paying to buy the credits, they may invest in their own technologies, okay, so as to reduce the carbon emissions. Okay, so the key point for the success of carbon reduction through the emission trading scheme is to set a low enough cap. Okay, you cannot distribute too many allowances in the market. Okay, if you're distributed many credits, many allowance to the market, then no one will invest in the clean technology. Okay, because there are many allowances, so a lot of supply, and the carbon price will be low. Okay, so you have to limit the numbers of allowances, okay, such that the carbon price is getting higher, then people will invest in clean technology. This is a video explaining the carbon markets.
Cap and pay is essential, and it's only made possible by data centers like ours. Goodman, essential infrastructure for the digital economy.
Companies are driven by money, so putting a price on carbon emissions should encourage businesses to stop polluting, right? That's exactly what carbon markets were designed to do, reduce emissions by charging polluters. But so far, they haven't achieved that aim. Here's why. Towards the end of the 1980s, America had a problem. For years, its power stations had been emitting large amounts of sulfur dioxide, which was falling back to Earth as acid rain, causing harm to plants, aquatic animals, and infrastructure. But there was no incentive for the power plants to stop emitting sulfur dioxide.
Weather warning on acid rain alert is in effect.
So in 1990, the American government launched an experiment, passing a law to force polluters to pay for their emissions by establishing a new kind of market, governed by a system called cap and trade. 8 years later, acid rain levels over large regions in Eastern America have fallen by 20%, and a new way of cutting emissions was born. In 1997, the International Climate Change Treaty, known as the Kyoto Protocol, suggested applying the concept of cap and trade to carbon. In the years that followed, different countries and regions set up their own carbon markets. Many of these use cap and trade, and this is how it works.
有牙齒變黃、牙邊變崩、敏感鼻痛，即刻轉用全新舒適達牙膏。
A government sets a cap on the amount of CO2 that can be emitted by an industry. It splits the cap into permits and either gives or sells these permits to firms. If a company doesn't use up all of its allowance, it can sell what it doesn't need. If it needs more permits, it can buy them from those with spares. Each year, the cap gets stricter, and the shrinking pool of permits gets more expensive.
The genius of cap-and-trade systems, when they're done properly, is that they both use a stick and a carrot. That gives them an incentive to innovate, to get cleaner and cleaner. It provides that carrot for innovation, and that trading mechanism, the magic of the market, unleashes those animal spirits in favor of decarbonization.
Though regulation can introduce a new industry standard, it doesn't give firms an incentive to cut emissions below a certain level. But a carbon market creates a race in which companies are motivated to cut emissions as fast as they can. The more they cut emissions, the fewer permits they have to buy, and the more excess they have to sell. So in theory, in a cap-and-trade market, carbon dioxide emissions should fall, but in reality, they've continued to rise, because incentives only work if they're big enough.
Carbon markets are great in theory, but in practice, we run into a problem. Carbon prices have been far too low to motivate change that's needed to decarbonize the world economy.
According to Joseph Stiglitz and Nicholas Stern, two economists, in order to meet the Paris Agreement goal of limiting global warming to 2 degrees above pre-industrial levels, the price of carbon worldwide needs to be between $50 and $100 per ton by 2030. However, the majority of carbon prices still remain far below that figure. What's more, even if carbon is priced appropriately, the fines for exceeding permitted levels are sometimes ineffectively low. In the EU, a fine can be as low as €100 per excess ton. Considering that's not much more than the price of a permit, it's hardly a deterrent. And that's if firms even get caught.
Now, in theory, regulators enforce carbon prices and permits, but in practice, it can be very challenging. There's measurement problems, direct emissions versus indirect emissions. There's questions of cheating, for example. You find in most markets around the world, enforcement is lax and punishment is not great.
大部分嘅人都唔知道琺瑯質酸蝕流失係會引致牙齒敏感。琺瑯質係牙齒第一個防線。我哋日常嘅酸性嘅食物都會。
And even if some markets adopt effective deterrents, the ones next door may not.
If we look globally, you have mind-boggling variety of rules, systems, enforcement mechanisms. And so if you're a company that's based in multiple countries, divisions of your company making the same product in the same way will face a mind-boggling patchwork of rules, regulations that differ. Worse than that, you have leakage among these markets as well.
The direct result of this patchwork of systems is known as carbon leakage. A business or an industry relocates from an area with high environmental regulations to somewhere where the rules are more relaxed, which means it can avoid having to pay for its carbon emissions. But these problems have solutions.
The role of regulation is important because absent regulation, nobody would pay for carbon emissions or pay a penalty for emitting carbon. So almost by definition, government has to create the market, set the rules, enforce penalties, set a carbon cap, for example, the maximum amount a company or industry can emit.
If governments limited the number of permits, it would drive their price up. Setting a minimum price that rises over time would mean the price would never fall too low, and governments could enforce more stringent deterrents for potential rule breakers.
Getting serious about regulating carbon markets really involves regulators making it clear to industry that they will not tolerate cheating, they will not tolerate leakage or obfuscation, and ultimately that they will hold corporate executives to account for their carbon emissions. I think we're getting there, particularly in the European Union. We're seeing much more seriousness, that this is not a frivolous greenwashing exercise, nudge, nudge, wink, wink, but rather that this is as serious as safety or other regulations. This is not yet the case in many other parts of the world.
It would help if the world had more integrated carbon markets, but as that's unlikely to happen in the short term, one solution to help prevent carbon leakage is a border tax. The EU has recently proposed to tax the carbon emitted in goods produced outside its carbon market. Importers would have to pay the same amount as if the goods had been made in the EU, meaning it wouldn't be any cheaper to source goods from a region with less regulation.
四周金大支，上上籤一開，好運自然來。針對修復琺瑯質，要先抗酸。原來日常酸性侵襲。
If we're going to get serious about dealing with climate change, within the next few years, we must achieve something like a global carbon price and some form of harmonization amongst economies. Now, we're getting to something like momentum in this direction. The big kahuna is China, because it's such an industrial powerhouse, it's so carbon intensive. If it doesn't get serious and work with other economies to harmonize carbon pricing and carbon trading systems, then most of the world's efforts will probably be undermined by the fact that countries like China are producing heavily carbon-intensive goods, and we'll see multinationals shifting production to those places even more than they have in the past.
As climate change has moved up the political agenda, governments are starting to improve how their carbon markets work. Since 2019, the EU has been taking steps to reduce the number of permits it hands out. Partly as a result, carbon prices in the EU are now hitting record highs of over 60 euros per tonne. Carbon prices in other markets are also rising as regulators look at ways to make them more effective. If it seems that money can be made, other countries might create their own markets.
We have seen just in the last 12 to 18 months a dramatic takeoff in carbon markets. This is a really exciting time for people who believe that there is a good marriage between public policy and regulators and markets and innovators.
If prices stay high enough, helped by commitments from governments and regulators, then greener industrial processes would become more attractive. And carbon markets could start to achieve their original goal of helping to decarbonize the world.
I'm BJ Vargas.
Okay, yeah, so this is a very good video explaining the essence of carbon markets. And so, yeah, we know that we want to reduce the carbon emissions, and there are many different approaches, okay, many different carbon embedment, like carbon reduction strategies, carbon reduction measures, okay, like energy efficiency improvement. Okay, I think the easiest way, okay, is to replace the fluorescent tube by LED. Okay, so this is a kind of energy efficiency improvement. Okay, light retrofits, or maybe utilizing some advanced technology, more energy efficient technologies. Okay, maybe like variable speed pump, variable frequency motor. Okay, so or yeah, some new technology in the building services systems. Okay, and we may also utilize renewable energy. Okay, solar panel, wind turbines, and others. Okay, transitioning to electric vehicles. So this is the electrification. So switching from using fossil fuel to using electricity, okay, and we may utilize some renewable energy for generating electricity, okay. Reforestation, okay, planting trees, and also, yeah, so trees are carbon sink, so it can absorb the carbon dioxide, okay, and then carbon reduction. And we may also like some sustainable agriculture. Okay, so instead of chopping down the trees for making paper, okay, so we give the forest some time to grow. Okay, some sustainable forest measures. And waste management, okay, reducing the solid waste, recycling, and then maybe we can utilize waste for generating electricity, okay, like capturing the methane in the landfill for generating electricity. And carbon capture and storage. So we capture the carbon dioxide and then store them underground or maybe under the ocean. So these are different carbon embedment measures. And maybe you can guess that some of these are particularly more expensive than others. Okay, like carbon capture and storage. Okay, very, very advanced technology, and there are risks. Okay, so it must be very expensive. Okay, and then the energy efficiency improvement. Okay, maybe just retrofit the LED, then yeah, very cheap, and you can also have energy saving, right? So different measures will have different cost effectiveness, and the amount of carbon reduction by the whole project will also be different. Okay, so in order to analyze which one is more cost effective, we may use some tools, okay, like the payback period, and also calculating the net present value, and maybe we can use some curves or some diagram, okay, to do the analysis. So we will learn all these in the lecture today. The carbon embedment measures. Equipment efficiency, the BIPV, new fuel or hydrogen fuel cells, and then the solar panel, wind turbines, smart glass, with the reflective properties. So these are some examples, and they have different costs. They have the amount of carbon reduction will also vary. So we want to do some financial assessment. So the financial benefits of implementing a carbon embedment measure is the potential savings on energy costs and carbon tax. Okay, so by reducing the carbon emissions, or maybe by reducing the energy consumption, then you can save the energy costs. And by doing that, if you need to pay for the carbon tax, then there would be some money saving too, okay, less carbon tax, as well as potential new revenue from the carbon market. Okay, so if you can reduce your carbon emissions so much and you have the extra permits, then you can sell it to the market, okay, to the ETS market. To determine whether the costs of implementing a carbon embedment measure are justified by the expected benefits, a financial assessment should be conducted. Okay, so for all these carbon embedment measure, okay, we want to use some tools to calculate or to estimate which one is more cost effective. Okay. So we have the simple payback. I think in the lecture 2 weeks earlier, we have learned the simple payback period already, and it is a non-discounting method. Okay, so we just assume $100 today is the same as $100 1 year later. Okay, so simple payback, very straightforward. And we also have some discounting method. So we take into the discount factor, okay, into our calculations. So discounting the time value of money. So it is based on the fact that the money you receive today will worth more than the money that you receive tomorrow, okay? Because everyone will have certain money earning power, okay? Maybe just put it in the bank, okay, in the saving account. You can earn interest, okay? So the money you receive today, you will worth more than the money that you receive tomorrow, okay? That's the concept of discounting methods. And for the discounting method, we may calculate the net present value, and we may also apply the net present value in the life cycle cost analysis. So let's first of all learn about the simple payback. So simple payback is a financial metric used to determine the time or number of years it takes for an investment to generate enough cash flow to recover its initial cost. So very easy, very simple equation. So just the initial investment. So on day one, how much do you need to pay for installing this equipment? Okay, and then divided by the annual cash inflow. Okay, like the annual savings. How much money or how much energy cost that you can save in a year, okay, then it will be the simple payback period, number of years that you can recover all these initial investment by the saving every year in the whole period. So we may rank the project based on how long income yields take to recoup the initial outlay. So the best project would be the one with shortest payback period, okay? And this simple payback is commonly used to evaluate the feasibility of projects, particularly in energy efficiency and renewable energy investment. So for energy efficiency program, you can save the energy. You can save the energy consumption, right? So like the light retrofit, okay, we replace the fluorescent tube by LED, okay, then less power consumption, less energy consumption, and therefore you pay less for the electricity fees. So it will generate some annual savings. So initial investment, the total amount of cost that you need to pay for the light retrofit, and then divided by the annual energy fees saving, then it would be the simple payback period. Okay, or maybe some renewable energy investment. Okay, like solar panel. Okay, you invest in the PV panel installation. Okay, you have to pay a lot of money, and then every year it has some energy saving. So once again, you can calculate the simple payback period. So of course, the shorter the number of years it takes to pay back the capital expended, the more favorable will be the scheme. Okay, the shorter, the better. But it does not accurately take into account the fact that money receivable in the future is worth less than the money you receive today. Okay, so in the simple payback period, we calculate the annual saving using today's unit rate of the electricity fees, okay? And it doesn't account for the fact that when you pay, the money that you pay today will be more than the money you pay tomorrow, okay? So for the simple payback period, it is not a discounting method. So it ignores the income received after, and it also ignores the income received after the end of the payback period. Okay, like maybe using this equation, the payback period for the LED light retrofit is 5 years. Okay, but after 5 years, there will be continue to be some energy saving. But in the simple payback period, it just ignores this energy saving, this amount of energy saving. So for simple payback period, apart from using this equation, it could be something like this. Okay, the annual saving may vary with years, with time. So let's say for project A, you have to pay for $1,000. Okay, $1,000 for initial investment. And then in year 1, you can save $200. And then year 2, save $300. And then year 3, you have to pay $100. Maybe for maintenance, maybe for some renovation. And then year 4, save $500. Save $300, save $100. Okay? So 1,000, okay? And then plus 2,000. So it will be negative 800. Okay? And then negative 500, and then negative 600, and then negative 100. Okay, and then in year 5 you will have positive 200. Okay, so that would be the time that these initial investment and the renovation or some maintenance fees will be recovered, okay, by the saving. Okay, so the payback period for project A will then be 5 years. And then for project B, just the same. Okay, we find out when will the initial investment be recovered by the savings. Okay. And next, we will explain the discounting method. Okay, we have kind of learned about the discounting method in the lectures 2 weeks ago. Okay, so the discounting method is a financial assessment technique used to determine the present value of future cash flows. Okay, for example, I know that by installing the PV panel, I can save maybe $1,000 for the energy cost every year. So this year, I save $1,000. Next year, I also save $1,000. And then 2 years, 3 years later, I also save $1,000. Okay, but the $1,000 that you save 2 years later, okay, will worth less than the $1,000 that you save today. Okay, because of the concept of discounting. So we want to calculate the net present values of all the saving in the coming years, and also all the costs that you have to pay in the coming years, so as to calculate the net amount of money, okay, and they are all in present value. So this method accounts for the time value of money, and recognizing that a dollar earned today is worth more than a dollar received in the future due to its potential earning capacity. Okay? So you will want me to give you $100 today, then $100 next week, right? You want to get the money now, okay, cash. Okay, so this is the discounting concept. Okay, so maybe now I give you this amount, and to you, okay, it makes no difference to, I should say, giving you this amount, a certain amount, and in some years later, okay, it will like giving you the same amount will means, or I should say, giving you the same amount 5 years later, okay, will worth less. Or if I give you the same amount of money, but 25 years later, then it means less and less and less. Okay, because you want to get the money now, such that you can invest, okay, maybe in the stock market. So $1 today worth more than $1 in the future. The discounting method involves calculating the present value of future cash flows by applying a discount rate. So you can treat the discount rate like the interest rate in the bank, okay? And something like that, okay, but not exactly the same, because every individual, every organizations have different investment or earning power. Okay, for me, I don't have much. Okay, I don't know the stock market, so I may just put the money in the bank. Then the discount, my discount factor would be the same as the interest rate in the bank. But maybe for you, okay, you know, you like to invest in the stock market and you can earn a lot, then your discount factor would be higher than mine. Okay, so every individual, every organization will have their own discount factor. So the discount rate or discount factor is the rate of interest reflecting the invested time value of money. Okay, so if you can invest the money in the stock market and then get a lot of profit, okay, so your discount rate will be higher, and it means that what you get today will worth much, much more than the money you get 1 year later, okay, because you can use these money you earn, you get now, and then invest in the market, okay? So discounting involves calculating the PV. PV is present value, okay? Calculating the present value of flows of money or flows of costs and benefits which are expected to arise at some time in the future. Okay, just like earlier when we learned about when we calculate the payback period. Okay, so we have some saving which will happen in year 1, year 2, year 3, in year 3, you have to pay for some costs. So these are all the money saving and the costs that will happen in the future. Okay, so this $200, you cannot get it now. Okay, you can get it only 1 year later. And then this $300, you cannot get it now. You can get it only 2 years later. And it means that because you can get this $300 2 years later, and it means if you convert it into the present value, it will be less than $300. Okay? And similarly, okay, $100, you have to pay $100 3 years later. Okay, but 3 years later, okay, not now. So if we convert it into the present value, then it will also be less. Okay, and the equation for calculating the present value is something like you put the money in the bank. Okay, like you have certain amount of money, and let's say you have $100 and you put it in the bank. So let's say you have 1% of interest, okay, and you put it in the bank like for 3 years. Okay, so this is the amount of money that you will get 3 years later, right? Okay, so this is the future amount of money. Okay, in the future, 3 years later, you can get this amount. And this $100 is the present value. Okay, it's the present value. So this 100 is the present value. And if you rearrange the equation, okay, it means that the present value will equal to the future amount of money that you will get divided by this. Okay, and in this equation, the 1% is the interest rate. Okay, but for me, the interest rate is just like my discount rate. Okay, so this equation is exactly this equation. Okay, so the present value will equal to the future money, and then divided by 1 plus the discount rate, and then to the power of t. T is the number of years. Okay, so applying the same equation, it means that, okay, like here, okay, you will receive $200 1 year later. Okay, and what is the present value? So this $200 is the future money. Okay, the future money that you will get. And then we put it in the equation. So D is the discount rate. So earlier I used 1%. And then the number of years would be 1. So to the power 1, like this. Okay, so this would be the present value of $200 that you will receive 1 year later. Okay, and it will be less than $200. Okay, because you're receiving this now. Okay, so you can put it in the stock market or put it in the bank to earn money. Okay, so $200 that you receive 1 year later will be yeah, can be using this equation to convert it into the present value. Okay, convert it into the present value. So it will be a bit less than 200. Okay, and similarly, okay, 3 years later, you have to pay $100, okay, but not now, 3 years later. So if you convert it into the present value, it would be, okay, the future amount of money, 100, and then divided by 1 plus the discount factor, and then to the power 3. Okay, to the power 3. So we may use this to calculate the present value of $100 that will be paid in 3 years later. Okay. And we have mentioned the discount rate, right? So my discount rate would be very small, maybe 0.00%. And then maybe for some of you, okay, maybe higher. So different discount rate will have different effects of the present value. So for this curve, okay, if you have $1 today, okay, then $1. But if you have it some years later and later, it will drop dramatically if the discount rate is higher. Okay, but if the discount rate is not that high, then giving me $1 is the same as giving me $1 1 year later, okay, because my discount rate is very small. Okay, but for you, okay, maybe your discount rate is very high. Okay, then giving you $1 today is the same as giving you $2 1 year later, okay, for example. Okay, so let's take a look at this case. Okay, what will be the future value of $1 invested today at a discount rate of 10%? Okay, like putting $1 in the bank. Okay, so current year means now. Okay, $1 is $1. Okay, but at the end of year 1, so after 1 year, okay, I put the $1 in the bank, and the bank gives me 10% of interest rate. Okay, and it means that 1 year later, I can get $1.1. Okay, because of the interest rate, right? And then 2 years later, I can get 1.21, and then 3 years later, this amount, and 4 years later, this amount. Okay, right? Just put the money in the bank. And it means that getting $1 now is the same as getting $1.1 1 year later, and also the same as getting $1.21 2 years later, or getting $1.46 4 years later. Same, okay, if your discount rate is 10%. Okay, so everyone will have different discount rate. Every organization, different company, different discount rate. Okay, but if the discount rate is 10%, then it will be like this. Okay, so the money you get now is actually better. Okay, so if you get the money later, then you need more money to have the same value. Okay? And what is the present value of $1 to be received in the future? So unlike earlier, so earlier is you get $1 now, and then you put it in the bank. And here in this table is that you get $1 1 year later, and you get $1 2 years later, and you get another $1 3 years later, another $1 4 years later. And you want to convert the $1 that you receive 1 year later into the present value, just like earlier in the table. Okay, you get $200 1 year later, or you need to pay $100 3 years later. So what would be the present value? We want to convert them into the present value. So receiving $1 1 year later is the same as, okay, using this equation, $1 and then divided by 1 plus the discount factor, and is equal to 0.91, so 91 cents. So it means that to you, okay, if your discount rate is 10%, getting $0.91 now is the same as getting $1 1 year later. Okay, it makes no difference to you, same value. Okay, and similarly, getting $1 2 years later is the same as getting $0.83 now. Okay, this $0.83 is the present value. Okay, so the longer time, the later that you get the money, the lower would be the present value. Because you have to wait long time to get that amount of money. You cannot invest it in the market. Okay, so the present value will be less and less. Right? Makes sense? Good. Okay. And on the right-hand side, we have some cumulative present value. So in after 1 year, so you get 0.91. And then after 2 years, if we add up these two, so these two present value adding together will be 1.74. And then these three values adding up together, 2.49. These four adding up together, 3.17. So it means if you expect to save $1 every year, okay, so by the end of year 1, I save $1. By the end of year 2, I save $1. And then by the end of year 3 and year 4, I save another $1. And then adding up, okay, converting all these into the present value and add them up, all of them, then the total will be 3.17. So it means getting $1 every year in the coming 4 years has the present value of 3.17 now. Okay, so it means giving you $3.17 now is the same as giving you $1 every year for 4 years. Good, okay? So just like the energy saving, okay, by retrofitting the using LED, okay, we can save some power, we can save energy consumption and therefore electricity fees. So we will expect every year we save certain amount of electricity fees. Okay, like here, saving $1 every year in the coming 10 years, and we may calculate all these into the total present value. Okay? So for this cumulative present value, we may use one equation to calculate. So earlier, this equation is for calculating the present value of a certain one-off amount that you receive in the future. And this value would be some cumulative present value. So every year you get certain amount for continuously 10 years, for example. Then we may use this equation to calculate. So it will be faster. Okay, we don't need to calculate the present value year 1 and then year 2, year 3, and then add them up. Okay, we just need to use one equation to do the calculation. So this AO would be the amount that you receive every year, just like the $1 that we mentioned earlier. So this is just like the $1 that we receive year 1, year 2, year 3, year 4. And then the discount rate is 10%. Okay, so this would be 0.1 for this D, and then 0.1, and then this D also 0.1, and N, 1, 2, 3, 4. So the number of years would be 4, and this one also 4. Okay, so we may use this equation, and if you use the calculator, it will equal to 3.17. Okay, So you don't need to calculate the present value every year and then add them up. Just use one equation to calculate the cumulative present value. And this equation is for recurring costs. Okay, the cost or the saving that will repeat every year. Okay, every year you save $1. Every year you save $1,000 for the energy fees. Then you may use this equation. Okay? And you may ask, so for the discount rate, like buying something, okay, like buying an iPhone, okay, you know that there is inflation. So today, maybe the iPhone is $6,000. Maybe 5 years later, okay, new model, then and there is inflation. Maybe it's more expensive, okay, like maybe $8,000, okay, because of inflation. And utility charge, okay, like for the electricity charge, there is also inflation. Okay, the utility charge may get higher and higher every year. Okay, then the discount rate needs to take the inflation into account also. So the effect of discount rate will be modified by inflation according to the following formula. So the 10%, okay, the 10% that we used earlier, okay, like in this equation, this D and also this D, okay, should be a discount rate that has taken the inflation into account. And we call this discount rate the real discount rate. Okay, so actually in this equation I should use DR. Okay, in this equation I should use DR to represent the real discount rate. Okay, and here this should be DR. Okay, we should use the real discount rate in this net present equation and also this cumulative net present equation. Okay, this should be DR, the real discount rate. So the real discount rate has taken the interest rate and the inflation into consideration. Okay, like for me, okay, I put the money in the bank and my discount rate is just like the interest rate. Okay, then this D maybe 0.0001. Okay, and then there is inflation. Okay, the inflation maybe 1%. Okay, so when you put this value into the equation, then you get the real discount rate. So to explain this equation, so let's say you want to buy an iPhone, and you know that you can only buy the iPhone maybe 4 years later. Okay, and you want to save the money. Okay, you want to save the money for buying the iPhone, and the iPhone that you want to buy maybe $8,000 now. Okay, maybe $8,000 now, and then you want to save some money such that 4 years later you can buy the iPhone. Okay, so this is the future money that you need to spend. Okay, 4 years later, I know that I need to spend $8,000, and maybe my discount rate is 3%, let's say. Then the present value of $8,000, okay, would be 8,000 and then divided by 1 plus 3%, and then 4 years. Okay, this is the present value of $8,000 after 4 years, right? But you know there is inflation. So let's say the inflation is 2%. So 4 years later, you will not be able to buy an iPhone by $8,000, okay, because there is inflation. So the inflation may be 2%. then you have to add, and 2% is yearly, okay, yearly percentage. So 4 years later, an iPhone will no longer be $8,000, but 8,000 plus 1 times, okay, 8,000 times 1 plus 2% and then to the power 4, okay, because of the inflation, right? So using this equation, we can rearrange it, okay, into 8,000 and then 1 plus 3% divided by 1 plus 2%, to the power 4. Okay, we just put this component to the lower portion. Okay, and then you can further rearrange it into 8,000 and then 1 plus 3% and then divided by 1 plus 2% minus 1, okay, and 1 plus to the power 4, right? Same equation. So 1 plus this and then minus 1 and then to the power 4. So it would be the same as here, right? So the lower portion, no change. Okay, then this part would be the real discount rate. So if we compare this equation with this equation that we have seen earlier, then this D, okay, would be this part. Okay, so this would be the real discount rate that has taken the inflation into account. Okay, so this 3 would be D, the discount rate, and this I, this 2 would be I, the inflation. All right. So let's go back to the same case study that we have seen earlier. So for project A, project B, we have different amount of money that you need to pay, and then different amount of money you can save. And we can convert all these future money into present value. It would be like this. Okay, so let's say the discount factor, the real discount factor is 10%. And these ratio, okay, would be, this discount factor would be 1 divided by 1 plus D, and then to the power N. Okay, N is the number of years. Okay, so let's say is year 1. Okay, then 1 divided by 1 plus 0.1. Okay, you can calculate 1 divided by 1.1. Okay, 1 divided by 1.1 is 0.91. Okay, that's the this value. Okay, and similarly 1 divided by 1.1 to the square 2 will be 0.83. Okay, so these are the future money. Okay, so except for the first row of the data, so you have to pay $1,000 now, so present value also $1, and 1 year later you can have a $200 saving. And if you multiply 200 with this value or this value, okay, then it will be 182. So it means receiving $200 1 year later is the same as receiving $182 now. Okay, so similarly for $300, it would be the present value, 249, and then present value. So we convert all these future money into present value. And finally, we can add up all of them. Okay, 1,000 plus 182 plus 249 and then minus 75 and so on. And the total will be negative 62. So it's a negative, and it means that after 6 years, there is no money saving. Okay, you still need to, there is still a net cost of $62. And for project B, also negative value, so it means there is still a net cost of $21. Okay, but yeah, this one is more preferable because higher value. Okay. So the net present value is used to evaluate the profitability of an investment or a project by calculating the difference between the present value of cash inflows and the present value of the cash outflows over a specific period. So in the example earlier, the specific period would be 6 years. Find the present value of all money inflows and outflows of the project considered. Okay, just like here, all the present value, and then find out the total. So if the value is positive, then it is a viable project, feasible project in terms of the economic value. Okay? Maybe we can take a short break of 5 minutes, and then we will study the life cycle cost analysis and also the marginal embedment curve. So let's take a break of 5 minutes. Okay, so let's carry on. So before the break, we have learned about the payback period, a simple payback period, and also the concept of discounting method and net present value. And for the earlier example, okay, we use 6 years as the study period. And we have ignored the fact that there will also be energy saving 6 years later, or maybe there would be some costs that you have to pay after this study period. So that's why we may use the life cycle cost or life cycle concept to study the overall cost for a project. So life cycle cost is the total discounted dollar cost of owning, operating, maintaining, and disposing of a building or a building system over a period of time. So the net present value or the life cycle cost analysis actually is not really related to carbon reduction. Okay, for any kind of project, you can do the life cycle cost analysis. It is not a must to be related to carbon reduction. So the life cycle costs comprise the assessment of the present value of the total capital cost, the financial cost, operational cost, maintenance cost, and the eventual disposal cost of the asset at the end of the lifetime. So in the example that we have studied earlier, okay, like this, the study period is 6 years. And then maybe on the 7th years, maybe there is another amount of maintenance fees you need to pay. And then maybe at the end of the lifetime of the project, okay, maybe you have to, maybe you can sell the equipment, okay, for generating revenue. Or maybe you have to pay to dispose the waste, okay. So in this method, in the simple calculating the net present value in this method, we didn't take into account the disposal value or the cost, the saving after the study period. Okay, so we may use the approach of life cycle instead. So here is the example. Okay, it is not related to the previous example. So another example. So let's say the study period is 20 years, and it means that we assume these original design, or maybe we have alternative 1, alternative 2, the life cycle would be 20 years. So after 20 years, we can no longer utilize the equipment and we have to dispose all the equipment. Okay, so we assume the lifetime is a length of 20 years. And we also have the assumption of the discount rate, okay, 15%. So this is D, okay, the simple discount rate. And we assume the inflation is 6%. So if you use the equation that we have explained just before the break, then the real discount rate will be 8.5%. Okay, that is using this equation. So 1 plus D divided by 1 plus I, the inflation, and then minus 1, and we have the real discount rate. So here, 8.5% is the real discount rate, or the composite discount rate. And we have 3 alternatives, or 3 designs, okay, 3 options. So this is the original, and then maybe these 2 are some energy efficient alternative, okay? And they have different base costs, installation costs, equipment costs, and also some single expenditure, maybe for renovation, maybe for some equipment replacement, and then there are some salvage. So you can sell the equipment, okay, so as to earn some money. So you see, it is negative when it is a saving or when it is a profit, okay? So life cycle cost, so this is the money that you have to spend. So unlike the example earlier, for the money that you need to pay is negative and the money that you save is positive, okay? But in the life cycle cost assessment, the cost that you need to pay will be positive. Okay, so you have to pay these amount and they are positive value. And when you sell the equipment, okay, after 20 years, okay, after or by the 16 years, you can sell some of the equipment. Okay, maybe you replace the old equipment with the new one, and then the old equipment can be sold to someone, okay, to earn the money. So the money that you save, the money that you earn will be a negative value. Okay, so similarly here we have some replacement fees, and then maybe you dispose the equipment and earn some money, so they are negative. And there are also annual energy costs. Okay, so annual energy costs, so these are the money that you need to pay for the energy fees, okay, for the energy fees, and then the money that you need to pay every year for maintenance. So these are annual costs. So you have to pay this amount every year, and then this amount every year, and these are also annual costs. Okay, so in the life cycle concept, we will list out all the costs that you need to pay over the whole lifetime. Okay, different kind of cost, the initial cost, installation cost, and then maybe renovation cost, or maybe disposal cost, or maybe energy cost, and so on. Okay, all these are costs, okay, positive. If they are negative, then they are saving or profit. So in order to calculate the net present value over the whole lifetime, we need to convert these future money into the present value, okay, using either this equation. Okay, if it is a one-off cost, then we use this equation. If they are annual costs, okay, recurring every year, like the energy cost, you have to pay certain amount for the energy fees every year, then we may use this equation. And using, just calculate once, then you can find out the total amount of recurring costs happen every year. Okay, the total, it will be over the whole study period. Okay, this number of years, n number of years. Okay, so we assume a study period of 20 years. The present value of yearly cash outflow can be calculated using this real discount rate. So we may use the two equations, the one highlighted in yellow color and the one highlighted in light blue color. So for the base cost, these will happen now, okay, year zero. So same, okay, they are same, but these, they will happen in the future. So we have to use the yellow equation, okay, the equation highlighted in yellow, okay, to convert it into present value. And N or T, okay, will be 16. Okay, this future money will happen in year 16. So the number of years, that T will be 16. Okay, and this amount happened in the future 16 years later. If we convert it into the present value, it would be this amount, right? And for the rest, just the same. Okay, use the equation highlighted in yellow. Okay, these also the one highlighted in yellow. But for these, they will happen every year. They are recurring costs. Annual energy costs, annual maintenance costs. So for these, we have to use the equation highlighted in light blue color. And N will be 20 years. Okay, every year you have to pay this amount. And for the future 20 number of years. So we use that equation highlighted in blue color. N will be 20. And then the real discount rate, 8.5%. And these are the future recurring costs. And the present value, the total present value over 20 years will be these, and these. Okay? And finally, you can add up all these costs. This is negative, okay, because it is a profit, and then these are also negative, negative, and negative. So if you calculate the total, then these are the life cycle costs. So in order to run the original design and then the alternative 1, alternative 2, you have to pay for these amount in 20 years. So over the 20 years, over the whole life cycle, you have to pay these amount of money, and they are the present value. Okay? So when all these costs are converted into present value, then we can compare them. Okay, the lower one will be the one that is more economic viable. Okay, you will pay cheaper. You need to spend less for installing this alternative 2, or for this design. And then for this one, alternative 1 is more expensive. Okay. So life cycle cost analysis is usually for comparing different alternatives. Okay, the absolute value may not be too critical, okay, because this inflation, this discount rate, this is only your assumption, right? You will not know in the coming 20 years what will be the inflation, what will be the economy, okay? So these are our assumption, but when we are comparing different designs based on the assumption, then this comparison will be more useful. Okay, so based on the same inflation rate, the same discount rate, the alternative 2 will be more cost effective. So many assumptions have been made in our life cycle cost analysis examples. So we need to check how sensitive are our results to the assumptions. For example, how sensitive would be the design to the discount rate? So we use 6%. So what if the discount rate is lower or higher? So how much will it affect the net present value? So to identify the critical parameters arrives at estimates of upper and lower bounds. Okay, we can do some sensitivity analysis. So answer the what if question, simply change the value of each input up and down, and then holding all other constant. For example, we want to estimate, or we want to analyze the sensitivity towards the annual energy cost. So we can recalculate the economic measure to be tested, and then study one of the factor. Okay, like this example, study the annual energy cost, and applying higher value, lower value. Okay, like higher 10% and lower 10% to the energy cost, and then calculate the net present value and plot them onto a graph like this. So we have the original design, we have the alternative 1 and alternative 2, okay, and we have used the energy costs of these. Okay, these are the annual energy costs. But these are only our assumption. So what if the utility fees getting higher, okay, because of the climate change impact, or maybe getting lower, okay, because of the available renewable technology. Okay, so we may we may set a higher energy cost and a lower energy cost and calculate the net present value over again. And the result, we plot them onto the graph. So if no change of energy cost, okay, so this would be the net present value for alternative 1, and then for original design, and then for alternative 2. But if the energy cost is cheaper, okay, then all the costs will be lower. Okay, so this would be the net present value of the life cycle cost if the energy cost is cheaper, okay, 10% cheaper. And then similarly, if the energy cost is 10% higher, okay, then we have these life cycle costs. And if you look closely to this graph, you may find that the slope of alternative 1 is steeper. Can you see that? The slope is larger for this orange line comparing to the blue and the green line. And it means that alternative 1 will be more sensitive to the change of energy costs. So if you are not very confident about the energy costs in the future, then alternative 1, maybe you have to be more cautious because this alternative is more sensitive to the change of energy costs. Okay, the final topic is the carbon embedment curve, or we can call it marginal carbon cost curve or carbon embedment cost curve. Okay, so yeah, marginal carbon embedment cost curve. It is an accounting methodology used to present graphically and in a quantifiable manner the investment performance of different energy reduction projects. The methodology ranks the various projects from the most cost-effective on the left-hand side to the least cost-effective to the right-hand side, okay, while illustrating the annual carbon embedded, or we say annual carbon reduction by each individual project. So if you think about what we have learned earlier, okay, the simple payback period, the net present value, or the life cycle cost, they have nothing to do with carbon reduction. It's all about cost effectiveness. But in the carbon embedment curve, we want to know how much do we need to pay for reducing every unit of carbon emissions. Okay, so this curve would be finally related to how effective is the carbon reduction strategy. So the carbon embedment curve will be something like this. Okay, the pattern would be something like this. So in the y-axis, it is the cost of each ton of carbon embedded. So it means if you want to reduce 1 ton of carbon dioxide equivalent, how much do you need to spend? Okay, and different strategy will have different costs. Okay, so maybe for retrofitting the lighting with LED is very cheap, or maybe for carbon capture is very expensive. Okay, so different mitigation strategy will have different costs of carbon reduction, right? Makes sense? Okay, and then in the x-axis, they are the annual carbon embedded. Okay, so annually, every year, how much carbon can be reduced by different kind of strategies. Okay, every kind of strategies will have a limit. Okay, you cannot reduce too much. Okay, like the replacing the lighting with LED, you have a limit, right? I have only 1,000 numbers of lamps in this building. Then, to the maximum, I can only replace with 1,000 numbers of LED lamps. Okay, so there will be a limit for the amount of carbon reduction. Okay, so for different projects, we can estimate the yearly amount of carbon reduction, and it would be in the x-axis. Okay, so for example, for this project or for this strategy, it is a negative value, and it means that you can save money and also reducing carbon dioxide. Okay, because it is a negative value, the cost is negative. So by using that mitigation strategy, you can save money. Okay, so for every 1 ton of carbon dioxide reduction, you can save this amount of money, and you can also reduce this amount of carbon in a year. So this certain ton of carbon dioxide equivalent in a year. Okay, so it means for this y-axis, if they are negative value, okay, the smaller the better. Okay, when this is a negative, then the lower the better, because you can save money, you can have profit by that mitigation project. And for the x-axis, the larger the better. Okay, or I should say, this is the amount of carbon that you can reduce in a year. So annual carbon embedded for this emission reduction project. Okay, so if the cost is negative, and then you can reduce a lot of carbon dioxide, then it is perfect, right? You can earn money, and then you can also reduce a lot of carbon dioxide, then it is perfect. Okay, so for this orange color, okay, the cost is negative, so it means that you can still save money, just not as much as this project, okay, and you can reduce large amount of carbon dioxide in a year. Okay, this is the extent of carbon dioxide reduction in a year. Okay, and we will arrange these projects from the best to, or the we will arrange them according to their cost effectiveness. So if the cost is the lowest, then we will place them on the left-hand side. Okay, and for the most expensive project with the highest cost of carbon embedded, then we will put it on the right. Okay, and it means that if you want to utilize the cheapest way to reduce carbon, you should start it from the left. Okay, so like your organization have a emission target to meet, then probably you have to you will implement the project on the left. And if not enough, okay, I have a very ambitious reduction targets, then you have to utilize this one, and then this one, and then also this one, and also this one, but still not adequate, still not enough. Then you have to spend some money on some technology. Okay, you have to pay for reducing the carbon until you can meet your target. Okay, or if the cost is too expensive, then you may compare the cost with the with the cost of the allowance in the emission trading market. So you can either buy the allowance from the market, or you invest in this technology. So that's why the carbon price have to be high enough such that the organization or the country will invest in more expensive carbon reduction technology. Okay, so just another example, the unit cost of reducing carbon, and then the x-axis is the annual carbon reduction. Okay, so the cheapest or the most cost-effective project will be on the left, and then the highest, the most expensive will be on the right. So for these projects, the cost is negative. So it means they offer a positive net present value. Positive net present value means that you can earn money. Okay, you can earn money within the lifetime of the project. So they are highly recommended. And then for these projects might be viable, might be feasible if the energy price increase, or you have to pay for the carbon tax. Okay, otherwise you won't want to spend any money in carbon reduction. Okay, only if there is financial incentive. Okay, for example, the carbon tax is more expensive than these costs, then you will rather invest in this technology, right? And these projects on the right-hand side, they are unlikely to ever be viable and should be rejected, okay, because they are just too expensive. Okay, so you will utilize these projects on the left first. Okay, use and benefits. So the marginal embedment cost curve analysis enables various asset management strategies to be considered and will improve the carbon mitigation performance of a facility, a process, or a building. And the analysis will utilize environmental benefits of different carbon mitigation projects. So in the carbon embedment curve, we can study how much carbon can be reduced. So unlike the payback period, unlike the present value is just about money, okay? But in the embedment curve, it's about how much impact can be reduced. I mean, the environmental impact can be reduced. So management plans can be created to implement the highest priority projects, which will be the projects on the left-hand side. Okay, so we will implement the projects on the left-hand side first. And whether identified as having the greatest environmental impacts, the most rapid return benefits on the investment, or a combination. So we can study, okay, whether you want to utilize the most cost-effective projects or the project that can give you much carbon reductions, okay, or in combination. So information from the marginal cost curve model will be displayed in a disaggregate form, allowing management to clearly see the financial returns and the carbon reduction benefits separately. So y-axis about money, and the x-axis about the environmental benefits. Various sensitivity analyses are used to show how the central estimates and assumptions are subject to change, just like the sensitivity analysis that we have done earlier. Okay, like the increase in energy price, the impact of the commodity price on maintenance and facility management, and development of environmental legislation bringing additional costs on building owners. So maybe the carbon tax, okay, the impact of carbon tax to whether you want to implement the projects, a range of appropriate solutions, and the anticipated return on investment over the lifetime of each solution will be recommended. So the marginal embedment cost curve is also very useful when it comes to pricing carbon. Okay, when you want to set a target of the carbon price. So the curve helps inform on where the price of the carbon allowance needs to go. So like earlier in this chart, okay, so if the carbon price is too cheap, okay, like cheaper than this amount, then people will just pay for the carbon tax or buy the allowance from the market instead of implementing this technology. Okay, so the carbon price should be higher than this value. Then the organization will invest in this technology and be able to reduce these carbon emissions. This is an example of MACC analysis that I found for New Zealand. And you can see different implementation or different reduction projects. And these are all negative. So they all have negative costs. And most of them would be about the transport. Okay, so these projects about the transport, and they can help you save money. Okay, so by implementing these projects without any cost implication, you will be able to save like 10 megaton of carbon dioxide every year. Okay, so for New Zealand, you can predict that every year it is very easy to save 10 megaton of carbon dioxide equivalent every year. Okay, and for the extra like 6 megaton, okay, from here to here, okay, the cost is not too expensive. Okay, maybe 20 to 30 New Zealand dollar for every ton of carbon dioxide equivalent. So not too expensive. And you will be able to reduce further 6 megaton of carbon dioxide equivalent. Okay, so by using this cost curve, the government will be able to predict how much carbon dioxide can be reduced and what are the cost implications. Okay, and for the rest, so if the government need to reduce further, okay, more carbon, then probably they need to invest more money into the project. Just some more example, so maybe for your reference. Okay, and in order to prioritize various energy efficiency options according to their cost effectiveness, an annualized cost divided by the carbon dioxide equivalent saving ratio is adopted. So we may use this equation to calculate this ratio. So actually this is similar to the y-axis, okay, the cost of embedment for every ton of carbon dioxide equivalent. So the annual saving and then or the annual cost that you have to pay with that design option. So design option and then minus the cost without the design. So this is the extra cost by implementing that project, and then divided by the extra carbon reduction in a year. Okay, so yearly cost, yearly reduction. Then you have the unit cost for every ton of carbon dioxide reduction. Okay, so let's take a look at one tutorial questions. So let's take a look at this tutorial. The following measures, so from number 1 to number 9, okay, so they are proposed for mitigating the carbon emissions in an existing office building, in some existing office buildings. So what you need to do is to calculate the life cycle costs and the carbon embedment potentials for the individual measures by assuming a 10-year lifespan. Discount rate 10%, and then the carbon dioxide emissions factor. So for every kilowatt hour of energy consumption, 0.55 kg of carbon dioxide equivalent will be released. So this is the emission factor. Okay, and the cost of electricity, okay, is the unit rate of electricity. So for every unit, every kilowatt hour, the charge is 0.747. And after you have calculated the life cycle cost, you also need to plot the carbon embedment curve. Okay, just like what we have seen in the PowerPoints. Okay, so find out all the life cycle costs and the saving, and then convert them into the net present value. And also to calculate the annual reduction in carbon dioxide emissions. Okay, then total cost divided by the total amount of carbon reduction in 10 years. Okay, we are assuming the study period is 10 years. So in this table, we have 9 different strategies. Okay, just like here. We have 1, 2, 3, 4, 9. Okay, 9 different strategies, and we want to plot a curve like this, or a graph like this. So various mitigation measures, you don't really need to know what are they. Okay, they are just A, B, C, D, G. Okay, and you have the initial capital outlays. So these are the initial costs. Okay, the initial costs. And by utilizing these measures, you can save energy. Okay, so reducing your energy consumption. So these are the carbon mitigation measures, and they can reduce the carbon emissions by saving energy consumption. Okay, so by paying this amount of money, installing these variable speed drive, then every year you can use less. How much? 1 million kilowatt hour energy. Okay, you can use less energy by this amount. And then for other, just the same. Okay, they have some initial cost and then the annual energy saving. And for number 8, this is the set point for the AC, for the air conditioning system. So maybe in the original set point is 24. Okay, now I increase, okay, raise the set point to 25.5 degree. Then you need to pay for anything, okay, just the set point. So there is no cost, but there would be certain amount of energy saving every year. Okay, that's the theory. So we have the initial cost, and these are already the present value. Okay, these are the costs that you have to pay in day 1, okay, now. And in the coming 10 years, you can save these energy, annual energy saving. Okay, so for each of these mitigation measures, we will calculate the life cycle cost. So in the solutions, we only explain the detailed calculations of the first mitigation measure, okay, just for number 1. But for the rest, the calculations are just the same. Okay, so for number 1, we have to pay this amount. Then every year you can save this amount of energy consumption. So first of all, let's calculate the recurring discount factor. Okay, so this equation would be the equation highlighted in light blue. This one. Okay, for the energy saving, it will happen every year in the coming 10 years. So they are recurring saving. So we may use this equation to calculate the net, the present value for the annual saving in electricity fees. So the discount rate is 10%. So D is 10%. So we put 0.1, 10% here. Then the discount factor for recurring costs will be 6.14. And it means if every year you have, you can save $100, okay, and then for the coming 10 years, every year you can save $100, okay, after 1 year, $100 saving, and then 2 years later, $100 saving, and 3 years later, $100 saving, and continuously for 10 years. And it means that in total, okay, over the 10 years time, you will be able to save $100 times 6.14. Okay, this would be the total amount of saving in 10 years. Okay, if every year you save 100. Okay, this is the present value of the saving. You see what I mean? Okay, so we may use this for the energy saving because the energy saving is an annual saving. Annual saving, and it means that they are recurring. Okay, they will happen every year. Okay, recurring cost or recurring money. Okay, so calculate this factor. And next, we want to find out the annual electricity charge. So the amount of energy that we can save is 1101.1362. So this is actually, I shouldn't put a dollar sign here. So this should be the kilowatt hour, and then multiply by the unit rate of $0.747 for every kilowatt hour. Okay, this is the unit rate for the energy, okay, for the cost of electricity. Okay, so this amount of energy saving multiplied by the unit rate of electricity, then this would be the electricity fees that can be saved every year, right? Okay, And this is for every year, and it will happen every year in the next 10 years. So if we multiply 6.14, okay, then this is the total amount of energy fees saved in 10 years, and they are the present value. Okay, the present value of the total electricity fees saved in 10 years' time. Okay? And next, we have to pay for this installation, right? So the payment, the cost would be this one, okay, 85 million, and they are already the present value. So we don't need to use any discount factor. Okay, these are already the present value. So we have costs that you need to pay, okay, and they are the present value, and you have the saving and also present value. So cost minus the saving, then you have the life cycle cost. Okay, so for the item one, over the whole lifetime, the net cost would be this amount. Okay, this is the net cost and is the present value. Okay, so this is the cost, and we also want to calculate the total amount of carbon dioxide that can be reduced in 10 years. So by saving this amount of energy, okay, this is the kilowatt hour, and by multiplying the emission factor, okay, which is kg of carbon dioxide equivalent, okay, so 0.55 kg of carbon dioxide equivalent for every kilowatt hour of energy consumption. Okay, so the total energy saved multiplied by the emission factor and divided by 1000, because we want to convert the unit kg into ton. Okay, then we will be able to find out the total, the annual amount of carbon dioxide reduction. Okay, by this number one, item number one. Okay, so this is the annual carbon reduction in tons of carbon dioxide equivalent. Oops. Okay. And next, in the carbon embedment curve, the y-axis is the cost of each ton of carbon embedded. So cost per unit of carbon reduction for every ton of carbon dioxide reduction. So we have the cost, okay, the net cost over 10 years, and then divided by the total carbon dioxide reduction in 10 years. So multiply by 10, because this is the total cost in 10 years. So we divide it by the total carbon dioxide reduction in 10 years. Then this would be the charge for, or the cost for every ton of carbon dioxide reduction. And this would be the y-axis value, right? This is the y-axis value. And how about the x-axis? The x-axis, so this length would be the annual carbon embedded. So every year, how much carbon dioxide can be reduced? So it will be this value. Okay, so this is the y-axis, and then this is the x-axis. Okay, so we can draw a rectangle, okay, for mitigation strategy number one. The y-axis value will be this 13198.7 $ for every ton of carbon dioxide equivalent reduction. Okay, this is the height of the rectangle, and then the width of the rectangle will be 605.9 ton of carbon dioxide equivalent reduction. Okay, so this is for the first mitigation strategy, and we can use the same method to calculate this value and this value for all the mitigation strategies. And the result is summarized in this table. Okay, so we have the initial cost, and they are already the present value. Okay, these are already the present value. And for the annual energy saving, this is the energy. So we can convert it into money saving by multiplying the unit rate. So 0.747. 0.747. Okay, then you can calculate the annual saving in electricity charge. But these are future money. Okay, these are future money. And you may convert it into present value. Okay, you can convert them into the present where is undo? Oh, 有冇人識點樣 unhighlight？ 有冇 undo 㗎？ Okay, anyway, so for this column, they are the present value, but for 10-year recurring savings. Okay, so I use this color because we will be using the equation highlighted in light blue color, this one. Okay, so by using this equation, we can convert this annual electricity fees saving into the total, the present value of the total electricity charge saved in 10 years' time. Okay? And the cost minus the saving, then we have the total life cycle cost. Okay, cost minus saving, 10 years' time. Then we have the net cost. Okay, the net cost. And we can also calculate the annual carbon embedded from the annual energy saved by multiplying the emission factor. Okay, by multiplying the emission factor, then you can convert energy consumption or energy saving into carbon reduction. Okay. And next, this is the total carbon reduction in 10 years' time. Okay, in 10 years' time. And the cost divided by the 10 years carbon dioxide reduction, and you have the y-axis. Okay, so this is the y-axis. Okay, and this is the x-axis. And for some of the strategy, like number 7 and number 8, they are negative value. Okay, negative value, and it means that you don't need to pay for the strategy. You can even have profit, okay, by applying or implementing that measures. Okay. So for all these different measures, we can calculate the unit cost for reducing every unit of carbon dioxide. And you can also calculate the annual carbon reduction. Okay, and plot in a graph. Okay, so the graph is like this. This is not the same as the one we seen earlier. So for this one, the cost is very negative. Okay, but here the cost is negative for this one and this one. Okay, but comparing to these, they are very expensive. And for this one, the negative is only like how much? So negative 500, negative 800. So this is for every 1,000. So this is 1. Okay, around 0.5. Okay, around 0.5 and then 0.8 and then 0.5. Okay, the cost. Okay, the cost. The unit is 1,000 Hong Kong dollar for every ton of carbon dioxide equivalent reduction. Okay, so this one is 0.5. Around 0.8. 0.835, and then this one is 0.4, how much? 96. Okay, and they are negative. Okay, and for this length, okay, this length from here to here, the length is, so for the best, for the most cost-effective strategy would be the set point 25.5, and we can save 382.1 ton of carbon dioxide equivalent every year. So 382. So this length would be 382. Okay, they are the best strategy. Okay, and we put the most cost-effective strategy on the left-hand side. Okay, so in this table, okay, we have the lowest value, set point 25.5. So this one will be put on the left, the leftmost, followed by LED, okay, number 7, and then the next one will be number 9. And the next one, number 5, and then the next one, number 3, and then number 1, and then number 6, and finally, and number 2, and finally, number 4. Okay? So after calculating these costs, you have to arrange them in terms of their cost effectiveness. Okay? So for the least value, for the most negative value, you will put it on the leftmost. Okay, and the length would be the annual carbon reduction. And for the LED, okay, the cost is negative $0.496 thousand for every ton of carbon dioxide reduction. And the total amount of carbon dioxide reduction in a year is 1,608. So this length would be 1,608 ton of carbon dioxide equivalent. Okay, annual carbon reduction. And the next one, heat recovery. Okay, number 1, I mean the first one, and then next one, and then this one. Okay, heat recovery. So the price or the cost is 2,000, so 2.4. So this one would be 2.4. Okay, and the width of this rectangle would be 430. Okay, so this length would be 436 ton of carbon dioxide equivalent. Okay, so the calculations is not difficult. Okay, so just calculate the net, the present value, convert the future money into the present value, and then find out the life cycle cost, the net life cycle cost, and also the annual carbon dioxide reduction. Okay, then you can find out the cost of every ton of carbon dioxide reduction, and also the and plot them onto the curve. And remember, you have to arrange the most cost-effective strategy on the left-hand side. Okay, so most cost-effective, and then less, and then less, and then on the right-hand side, these would be the strategies that is most expensive. You have to spend a lot of money in order to reduce every ton of carbon dioxide. Okay, any questions so far? All right, so if no, I will just stop here. Okay. And then, yeah, next week we will continue. All right, so see you next week.